Good morning, students. In the previous class, that is class 3 of the chapter Chemical Kinetics, already covered. That is molecularity of a reaction, characteristics of a molecularity, types of a molecularity, then the difference between molecularity of a reaction and order of a reaction. Next, the first long question of the chapter, that is the kinetics of zero order reaction. Today, in class 4 of this chapter, I will try to cover next second long question of this chapter, very important for council point of view, that is kinetics for first order, and some formula and some problem relating to zero order and first order. So before going to the kinetics second long question, that is kinetics of zero order, I go through a recap, that is long question and some points regarding to zero order kinetics. Already covered, that is the expression, mathematical expression is, that is K is equal to 1 by T A naught minus A. It is the required expression for zero order kinetics in integrated form. Then, by putting initial A naught is equal to A moles per liter, by putting A naught is equal to A moles per liter and A is equal to A minus X moles per liter, the above equation can be transferred that is A is equal to X by T. It is the required expression for zero order kinetics in normal form. Then another one is that if we go through find out the rate constant for zero order kinetics in graphical mode, mark that this equation is rearranged as, mark that Kt is equal to A naught minus A. Rearranging this one is A is equal to A naught plus minus K into T. So it is an expression, equation of a straight line in the form of y is equal to mx plus c. This one is y, it is m, it is x, it is c. So if we plot a graph by taking y versus x, y, that is concentration, final concentration versus a time period, we have a graph like this. This is known as y-intercept, that is A naught, and while slope m is equal to, what is slope? Minus k. It is the first graphical representation. And since it is a zero order kinetics, means by definition, rate does not change with concentration. So if we go through the second graph, by rate versus concentration, that is the graph. Next we discuss about half-life period. What is half-life period? It is represented by the symbol half-life, that is T1 by 2. It is the time during which the concentration reduced to half of its initial value. That means when T is equal to T half, the initial concentration A naught, is equal to A naught by 2. So putting this value in this equation, we have K is equal to 1 by T half, here A naught minus A naught by 2. So this equal to our K is equal to, it is A naught by 2 T half, or T half is equal to A naught by 2K. So this equation is a required expression relation with half-life period and initial concentration. So if we plot a graph by half-life with initial concentration, we relate that half-life period is directly proportional to initial concentration. And this equation may also be represented as, mark that T half is equal to A naught into 1 by 2k plus 0. It is an equation of a straight line in the form of y is equal to mx plus c. Mark that it is y, it is m, it is x, it is c. Y is equal to mx plus c. So if we plot a graph by taking y versus x, means t half versus initial concentration, mark that the graph is this one, because y-intercept is 0. Here a slope m is equal to 1 by 2k. So these are the little bit idea about recap about zero order kinetics. So next we will go through some problems relating to zero order kinetics. Next we will switch over to the second long question, that is first order kinetics. Mark that one problem is there. Question: the rate constant for a zero order reaction is 4 moles per liter per second. According to the question, the rate constant for a zero order reaction is 4 moles per liter per second. Calculate the time required to reduce the concentration of the reactant from 2 mole to 1 mole. That is 2m to 1m. So from this equation, from this question, it is clear that answer. What are the data given? Data given is k is equal to 4 moles per liter per second. A naught is equal to 2m. A is equal to 1m. So find out the time t is equal to question mark. So if we apply this data to this formula, that is t is equal to 1 by k a naught minus a. So put this value, that is 1 by 4 into 2 minus 1, that is 1 by 4 second. It is a 2-mark question relating to zero order kinetics. Next we go to another question relating to order of reaction. Another question is there. Mark that. What is the question? A reaction is first order with respect to A and second order with respect to B. Next question. A reaction is found to be first order with respect to A and second order with respect to B. Then calculate the change in rate. Calculate the change in rate when between molar concentration of B is increases 3 times and B2 molar concentration of both A and B increases 2 times. Mark the question, I repeat again. A reaction that is given, it is the first order with respect to A and the second order with respect to B. That means answer. We have to represent, first we represent the rate expression. According to rate law, the rate expression is equal to R into K into A B to the power 2. Mark that. Then question is that bit 1, molar concentration of B increases 3 times. That means R1 is equal to K A, that is 3B to the power 2. This equal to 9K A B to the power 2. That means 9R. So from this expression it is clear that if molar concentration of B increases 3 times, rate increases 9 times. Move to the second bit. If the molar concentration both A and B increases 2 times, then next new representation R2 is equal to K 2A 2B to the power 2 is equal to 2 to the power 4 to 8 into K A B to the power 2 indicates that 8R. So if we make a comparison between this first one, it is the second one, it is the third one. So if we make a comparison with equation 1 with equation 2, it is clear that if both the molar concentration of A and B increases 2 times, the rate increases 8 times. It is a little bit idea about the order of a reaction and how order is related to rate of a reaction. Next, switch over to the important one, the second long question, very important one of this chapter, that is kinetics of first order reaction. Next we discuss long question, that is kinetics of first order reaction. What do you mean by first order reaction? A reaction is said to be first order if during the reaction only one reactant molar concentration term involved in the rate determining step, or the sum of the molar concentration, sum of the power of the molar concentration term raised, which is represented in rate law expression, each one. Then it is known as first order kinetics, first order reaction. So let us consider a first order reaction. Let us consider a first order reaction A give rise to product. Let us consider a first order reaction A give rise to product. Let us suppose the initial concentration of A is small a moles per liter. And during the time period, when time period increases, during the progress of the time period, reaction proceed. Means concentration of reactant gradually decreases, consumed, while concentration of product gradually increases. So suppose after time small t second, X moles per liter, that the concentration of A is decomposed to give the product. And after time t, suppose let the product concentration is A minus X. So this is represented mathematically, mark that. At time t is equal to 0, it is A moles per liter and product is 0 moles per liter. At t is equal to 0 means reaction does not proceed. At that time, that is initial state. Suppose the molar concentration of A is A moles per liter, and since the reaction does not proceed, so there is no product. Product concentration is 0. So after time small t, that is after time small t second, what happened? Small x moles per liter of the concentration of reactant is consumed, decomposed. So what is left? A minus x moles per liter. And what is the product concentration? X moles per liter. Mark that. It is the initial condition, it is the final condition. Initial condition, let us consider the initial concentration of reactant A is A moles per liter and concentration of product is 0. After time t, not given, let us any interval of time t. So in X moles per liter in concentration of the reactant is decomposed. So what is left? A minus X moles per liter, and that decomposed loss is transferred to the product side, and at that time the concentration of product is small x moles per liter. Then according to the first order of kinetics, rate, that is R, that is dx by dt directly proportional to what is left after time t, that is dx by dt proportional to a minus x. If we remove a proportional sign, then we have to put equal and proportionally constant, or dx by dt is equal to k into a minus x, where k is a proportionally constant, or if we rewrite, that is dx by a minus x is equal to k into dt. Equation 1. Rewrite the above equation. This a minus x moves to this side, dt transfer to this side. So dx by a minus x is equal to k into dt. Next, integrating both sides of this equation 1 we have. Mark that. Integrating both sides of the equation 1 we have. If we integrate both sides, what do we observe? Integration of dx by a minus x is equal to k into integration of dt is equal to minus integration of dx by a minus x is equal to minus ln a minus x is equal to kt plus c, equation 2, where c is known as a constant, proportionally constant for the first order kinetics. Mark that. We have to find out the value of c. Mark that. When t time period is equal to 0, when the reaction does not proceed, there is no loss in concentration of reactant, means x is equal to 0. When reaction does not proceed, t is equal to 0, that is at initial condition, there is no loss in concentration of reactant, that is x equal to 0. So putting this value in above equation, putting this value in above equation, we have, mark that, minus ln a minus 0 is equal to k into 0 plus c. That means c is equal to minus ln a, equation 3. Now, putting the value of c from equation 3 in equation 2, we have, mark that, putting the value of c from equation 3 in equation 2, we have, mark that, what is the value? Minus ln a minus x is equal to kt minus ln a, or this one transfer to this side, kt, or kt is equal to, this one transfer to this side, ln a minus ln a minus x. Mark that. Kt remain as such, this one transfer to this side. So ln means logarithm base e. So logarithm base e, if you transfer to logarithm base 10, mark that log a minus log b is equal to log a by b, or kt is equal to ln a by a minus x, or kt is equal to ln base e transfer to log base 10, that is 2.303 into log base 10 a by a minus x, or k is equal to 2.303 by t log base 10 a by a minus x. This is the required expression. This is the required expression for first order kinetics in normal form. This is the required expression. Equation 5 is the required expression for first order kinetics in normal form. It can be transferred to integrated form. This above equation in normal form can be represented in integrated form by putting the above equation can be represented in integrated form by putting A, that is initial concentration, is equal to A naught, and A minus X, that is final concentration A. By putting initial concentration is A naught and final concentration A in the equation 5, we have. Mark that, what happened? That is k is equal to 2.303 by t log base 10 a naught by a. This is the required expression. This is the required mathematical expression for first order kinetics in integrated form. Equation 5 is the required expression for first order kinetics in normal form. Equation 6 is the required expression for first order kinetics in integrated form. So from this equation 5 also, we can represent graphically, we can calculate the value of rate constant graphically. Mark that, how it is possible. Graphical representation. To calculate the value of rate constant for first order kinetics. So before going to that, I recap the again equation. What is the final equation? That is k is equal to 2.303 by t log base 10 a by a minus x. This is the required expression for first order kinetics in normal form. By rewriting this one, this t transferred to your marker, or kt by 2.303 is equal to log base 10 a by a minus x. Log a by b is equal to, log a minus log b is equal to log a by b, or kt by 2.303 is equal to log base 10 a minus log base 10 a minus x. Mark that. Again rearranging the above equation. We have, mark that, or this term transfer to this side, or log base 10 a minus x is equal to log base 10 a. This term is moves to this side, minus k by 2.303 into t. Mark that. This term moved to this side, so log a minus transfer to plus log 10 a minus x. This one remain as such. This term moves to this side. So plus transfer to minus, minus inside. I represent this one. Why I represent this one? It is an equation of a straight line in the form of y is equal to mx plus c. Mark that. This one is y, it is c, it is m, it is x. It is an equation of a straight line in the form of y is equal to mx plus c. That means if we plot a graph by taking y versus x, mark that. If we plot a graph by taking y versus x, what is y? That is log base 10 a minus x, y, versus x. What is x? That is a time period. Then the graph is like this one. This one is known as y-intercept. What is y-intercept? That is log a. Then what is the slope? Slope. What is the slope? Slope is m. M is equal to minus k by 2.303. Minus k by 2.303. Mark that. That means from this expression it is clear that if slope of a line is given, then we can calculate the rate constant or velocity constant simply by multiplying this one. It is a graphical representation for calculating the rate constant and also calculating the slope for the first order kinetics. And as it is a first order reaction, that means rate is directly proportional to the initial concentration, the power 1. Only one reactant concentration change. So again, if we plot a graph by taking rate versus concentration, rate versus concentration. As it is a first order kinetics, increasing the concentration increases the rate. It is the expression rate versus concentration for first order kinetics. Next we discuss half-life period for a first order kinetics. Half-life time or half-life period. Symbol is T1 by 2 or T 50%. Mark that. What do you mean by half-life time? Already covered, that is in zero order kinetics. Same definition is there. It is defined as the time period during which the concentration reduced to half of its initial value. I repeat again. It is defined as the time period during which final concentration is reduced to half of its initial value. It is a time during which final concentration is just half of the initial value. That means when T is equal to T half, initial concentration, that is A, becomes A by 2. So putting this value in our previous equation, what is the previous equation? That is K is equal to 2.303 by T log base 10 A by A minus X. That means when T is equal to T half, what is lost? In previous case, as a time is not mentioned. We say that X moles per liter is decomposed. but now time is mentioned. So that loss, that is, what is the loss? X moles per liter, that is fixed. What is that value? Half of the initial. That means X is equal to A by 2. So putting this value in equation, we have putting this value in above equation, we have mark that K is equal to 2.303 by T half into log base 10 A by A minus A by 2. Mark that K is equal to, or K is equal to 2.303 by T half. This one is equal to log base 10 A by A minus A by 2 is equal to A by 2. A by 2 is equal to 2.303 by T half, that is log base 10, that is 2 into A cancel log 2. We know the value of a log 10, log base 10 2 is equal to 0.3010. By putting this value in equation, above equation we have, that is K is equal to 2.303 into 0.3010 by T half, or K is equal to 0.693 by T half, or T half is equal to 0.693 by K. Mark that. So from this expression it is clear that half-life period of a first order kinetics is independent of initial concentration. So from this expression it is clear that half-life period of a first order reaction is independent of initial concentration. So if we plot a graph by taking half-life versus initial concentration in moles per liter, the graph is like this one, because it is independent. Whatever may be the concentration changes, there is no change in half-life period. So it is a straight line, that is perpendicular, it is a straight line parallel to x-axis. Next we go through some characteristics of first order kinetics. Next we discuss characteristics of first order reaction. 2 to 3 points are there. Point 1, mark that. All the first order reaction must obey this reaction. What is the reaction? That is K is equal to 2.303 by T log base 10 A by A minus X. All the first order reaction must obey this one. Next point, that is half-life period. Already we discussed. Second point is half-life period. So from this half-life period it is clear that half-life time for a first order reaction is independent of initial concentration. Mark that. That is half-life period of a first order reaction is independent of its initial concentration. Next, another point, third point. If we go through the calculating for time, unit of rate constant, we know unit of rate constant, that is K for first order reaction. In previous class already discussed, that is unit of rate constant for nth order, that is K is equal to moles per liter to the power 1 minus n dot second inverse. N is known as order of reaction. As it is a first order, put the value n is equal to 1. So 1 minus 1, 0. This term will cancel. So unit is second inverse. The unit of rate constant for first order kinetics is the second inverse. That means from this relation it is clear that the rate constant for first order reaction does not related to initial concentration. The unit of initial concentration, it is only depend upon the time. So if time is expressed in second, so it is unit is second inverse. In minute inverse. In hour inverse. Next we discuss some relation relating to the first order kinetics. Before going to calculating some relation, one term is there that is known as average lifetime. Average lifetime. Symbol is tau. We discussed previous one is half lifetime, another one is the average lifetime. Mark that tau. It is the reciprocal of rate constant. This one is the reciprocal of rate constant. If we put the value of rate constant, we know that by putting this value, this is equal to, we know K, that is 0.693 by T half. So this one equal to T half by 0.693 is equal to, that is 1 by 0.693 into T half. This is equal to 1.44 into T half. That is, the relation is there. What is the relationship? Relationship is that is average life is equal to 1.44 into half life. This one the expression relation for average life and half life for first order kinetics. Next we will go through some relation relating to the first order kinetics. Amount of substance left after n half life, 1 half life, 2 half life, 3 half life, after nth half life, what fraction of substance left? A formula is there, that is n is equal to n naught into 1 by 2 to the power n, where n is equal to final amount, n naught is equal to initial amount. Either you represent final concentration or initial concentration, or final amount, initial amount, and the small m is equal to number of half life. 1 half life, 2 half life, 3 half life, number of half life. Again another formula is there. How we calculate the number of half life? That is n is equal to t by t half. Another formula is there. Mark that. How you calculate the number of half life is equal to capital T by t half. Again, where capital T, that is total lifetime, and T half is equal to half lifetime. Mark that is the relationship. What fraction of substance left? What fraction of substance left after time T? How we calculate? That amount present initially into 1 by 2 to the power n. This small n represent number of half-life. How you calculate the number of half-life? That is n is equal to total lifetime by half-lifetime. Another relation also there, that is how half-life time depends upon the concentration. How half-life time depends upon initial concentration. Expression is that is a T half directly proportional to a to the power 1 minus n. This is one expression. T half directly proportional to a to the power 1 minus n, where T half is known as half lifetime, small a is known as initial concentration, and n is known as order of reaction. Then we discuss some another expression relating to the first order kinetics. That is some usual relation for first order kinetics. Point 1, T75, or it is known as T3 by 4. T75 means it is a time during which 75% of initial concentration is consumed. That is equal to 2 into T half. Mark that. It is one expression. Next, T 99.9% is equal to 10 into T half. Next, T 99.9% is equal to 5 into T 75. Mark that. These are also relation. These are also formula and also one problem, 2 mark question. Suppose this is one formula is there and also one question. That is, it may be question direct prove that T75 is equal to 2T half, 2T50, or in language mode, prove that the time required for the completion of 75% of a first order reaction is equal to nearly double that of the half-life time. Similarly, prove that direct relation T 99.9 is equal to 10 T half, or in language mode, prove that the time required for completion of 99.9% of a first order kinetics is nearly equal to that of 10 times of its half-life period. Similarly, another relation also there, that is T 99.9% is equal to 3 into T 90. Another also there, another relation, that is T 99% is equal to 2 into T 90. Mark that. These are some relational and also the problems. Each one is a 2 mark problem. Let us solve one or two, one by one. First one, that is T75% is equal to 2T half. That means the time required for completion of 75% is nearly 2 times that of the half-life period. We have to prove the first one, that is T75% is equal to 2T half. Answer. We know by definition T75% means 2.303 by K log base 10 A by A minus X, A by A minus X. Here A is initial concentration, always taken as 100, and X, that is 75, what is the loss? So I rewrite this one, that is 100 by 100 minus 75 is equal to 2.303 by K log base 10, it is 25, it is 4. That is 4 rewrite as 2 to the power 2, that is 2 log 2. That is 2 into 2.303 by K into log base 10 2. This is equal to, by putting this value, we know the value of log 2 is equal to 0.3010. Putting this value, this one equal to 2 into 0.693 by K, equation 1. Next we know that T half, another one relation is there, T half. What is T half? We know, again, we know that is T half. T half is equal to 0.693 by K. Mark that. Or K is equal to 0.693 by T half. Putting the value of K from equation 2 in equation 1. Putting the value of K from equation 2 in equation 1, we have, mark that. That is T 75% is equal to 2 into 0.693 by this value. 0.693 by T half means into T half. This one cancel. That means T 75% is equal to T half. That is a 2-mark question. This question may be direct. Prove that this in language, in word form, or in language mode. Prove that the time taken for completion of 75% of first order reaction is nearly equal to, that is 2 times of half-life period. Similarly also, we can solve another problem. Next we go through another type of problem. Next question is half-life time of a first order reaction is 69.3 seconds. Calculate the time required for completion of 90% of it. Mark that. What is the data given? Data given, half-life time is given. Answer. Given that T half is equal to 69.3 seconds. What is the question? Question is calculate the time. We have to calculate the time. That is T is equal to 2.303 by K into log base 10. Always A is 100. 100 minus time is given 90. Again, by putting the value of K, we know the value of K. Value of K is for first order reaction is value of K is 0.693 by T half. Putting this value 2.303 by 0.693 by T half into T half into log, it is 10. 100 by 10 is 10. Mark that. Log 10 is 1. So this one I rewrite. That is T is equal to 2.303. Half-life given, that is 69.3. This one is 0.693. So can you cancel this one? Mark that. That is 2.303 by into, it is 693 by 10, it is 693 into, cancel, that is 0 cancel, to 30.3 second. So the time required for completion of 90% is 230.3 seconds.